Welcome back to the deep dive. Today we're doing something a little different. Usually, we take a polished article or best-selling book or some piece of cutting-edge research and we break it down. But today we're virtually stepping right into a classroom.
And not just any classroom. We're dropping directly into the middle of a master's level chemical engineering course.
Right. And look, before you hit skip, because you hear chemical engineering and immediately have those like high school flashbacks of memorizing the periodic table or staining your shirt with Bunsen burner soot, just stick with us. Because this isn't about memorizing facts at all. This is about, well, it's about hacking reality.
That is a pretty bold way to put it, but honestly, it's accurate. We're looking at a recording that teaches us how engineers use computers to solve problems that are effectively impossible to do with a pencil and paper. It's really about the shift from just doing math to actually building models.
And the context of this specific recording is, it's just as gripping as the math itself. We aren't sitting in some high-tech lecture hall at MIT or Stanford with perfect acoustics and climate control. The recording is from Ukraine.
Yeah, it's a university practical session recorded right in the middle of the war.
It is incredibly grounding to listen to. You have this professor who sounds remarkably calm, teaching high-level mathematical modeling. But in the background, or really in the subtext of the whole conversation, he's dealing with the power grid completely fluctuating. At one point, he actually warns the students that his voltage just dropped to 170 volts.
It's intense. He warns them the internet might cut out at literally any second because there is active shelling near Rivne. He's sitting there looking at his modem, just hoping it stays on long enough to explain how to optimize a reverse osmosis unit.
It really puts the whole thing in perspective. He is essentially telling them, okay, the lights might go out, the internet might crash, rockets are flying, but we still need to figure out the stoichiometric coefficients of this reaction. It's this surreal mix of gritty, everyday survival and just pure, high-level intellectual abstraction.
Which, if you think about it, is kind of the ultimate engineering challenge anyway, solving incredibly complex problems under extreme life or death constraints. It really sets the perfect tone for this master's level mindset we're going to be talking about today.
Exactly. So here's our mission for this deep dive. We're going to unpack two very different but strangely connected themes from this lecture. First, we're going to look at the math itself, specifically how this professor teaches his students to use Excel to hack chemistry using matrices.
It effectively turns chemical reactions into a logic puzzle that the computer can just solve for you.
Right. And second, we're going to take a pretty hard pivot into philosophy. Because right at the very end of the class, the professor drops this heavy wisdom about how we learn new languages and, frankly, how we learn anything complex. And he explains why your Netflix habit is basically entirely useless for your brain.
That part is definitely going to hurt some feelings, I think, but he makes a really compelling case.
Oh, absolutely. Let's start with the math, though. And I want to be clear for everyone listening, we aren't just talking about doing basic sums here. The course is technically about applied mathematics.
Correct. And that is a crucial distinction the professor makes very early on. He draws a really hard line between calculation and modeling.
Walk me through that. Because to me, if I'm adding numbers up, I'm calculating. And I'm doing math, I'm calculating. What makes modeling actually different?
So think of calculation as crunching numbers to get a single highly specific answer. Like if I ask you to solve a quadratic equation to find the discriminant, you follow a set rule, you plug in the specific numbers, and you get a result. It's rigid. It's a one-off task.
Okay, like figuring out how much tip to leave at a restaurant. That's a calculation.
Exactly. Modeling is totally different. Modeling is when you take a messy real-world system like a chemical plant or a traffic jam or even a weather system, and you abstract it into a mathematical structure that mimics how that system behaves over time or under totally different conditions. You aren't just looking for an answer, you are building a simulator.
So calculation is asking what is 2 plus 2. Modeling is asking how does this entire machine work if I swap out this one gear?
Precisely. And in this particular session, the students are making that transition. They had been doing basic calculations in Python previously, finding roots of equations, simpler stuff. But now they are moving to stage 2. They are tasked with modeling a reverse osmosis unit.
Reverse osmosis, just to make sure we're on the same page. That's the high-end water filtration stuff, right? Pushing water through a really tight membrane to get the salt out.
That's the physical reality of it, yes. It's used in desalination plants, municipal water purification, even up on the space station. But the professor's point isn't really about the water or the salt at all. It's about the architecture of the model. He talks a lot about a bottom-up approach versus a top-down approach.
And he clearly prefers the bottom-up way for building these specific models. He tells them, do not try to build the whole plant at once.
Right, because if you try to model a massive filtration plant with 1,000 pumps and pipes and filters from scratch, you will fail. There are simply too many variables. You'll get entirely lost in the noise. So he tells them to model one unit, just one filter, one pump. Get the logic of that single brick absolutely perfect.
And once that single brick is solid,
Then you just copy and paste it. You go from a single-stage system to a two-stage system. If your underlying model, your brick, is fundamentally sound, you can scale that up to a system with 1,000 components without breaking a sweat.
it's the Lego philosophy of engineering. You don't try to mold the whole castle out of plastic, you just stack the bricks.
It really is. It's all about modularity. And to really hammer this modeler's mindset home, he references a classic textbook on applied mathematics by Mishkis and Zeldovich. These guys are absolute titans in the field, and he brings up their absolute favorite example of a system:
The toilet tank.
the humble toilet tank.
I have to say, when I think of complex mathematical engineering or master's level science, I really do not think of the thing I have to scrub every Saturday.
But see, that's because you're looking at it like a consumer. You just see the porcelain in the water. The professor explains that to a mathematician, a toilet tank isn't a bathroom fixture at all. It is a capacity with a level regulator.
Capacity with a level regulator. That is definitely the most unromantic, dry description of a toilet I've ever heard in my life. I love it.
It is dry, sure. But think about the sheer power of that abstraction. When you strip away the ceramic and the handle and the chain, what do you actually have left? You have a storage volume, that's the capacity, and you have a feedback loop, the regulator, that shuts off the input when the volume is completely full.
Okay, so it's a system that self-corrects. It fills up, the little floaty thing rises to the top, and it mechanically shuts off the water.
Exactly. And here's the real kicker. The math you use to describe that toilet tank, the differential equations describing flow, capacity, and feedback, is the exact same math you use to describe a chemical reactor vessel, or a fuel tank on a SpaceX rocket, or a massive hydroelectric dam reservoir.
Wow, so by learning the math of the toilet, you are accidentally learning the math of the rocket ship.
That is the whole beauty of applied math. Once you abstract the real world into these pure systems, the skills transfer everywhere. You stop seeing objects entirely. You start seeing structures. You realize that a toilet and a nuclear reactor actually share the exact same DNA, mathematically speaking.
That's a genuinely powerful way to look at the world. And it frames the next part of the lecture perfectly, I think, because they move from modeling water flow to something much, much messier: stoichiometry.
Ah, yes. Balancing chemical equations.
This brought back some legitimate high school trauma for me. Just sitting there at a desk, trying to make sure I have the exact same number of oxygen atoms on the left side of the arrow as I do on the right side. It always felt like I was just blindly guessing.
It's all based on the law of conservation of mass. Matter cannot be created or destroyed. If you start the reaction with 10 grams of carbon, you absolutely have to end with 10 grams of carbon. It just might be attached to a completely different molecule now.
Right. And the professor makes the point that if you're doing a simple reaction, like making ammonia, you can pretty much just do it in your head. Or jot it down on a napkin. It's basic algebra.
But then he brings up oxidation-reduction reaction. Redox reaction.
Why are those ones so much harder to do by hand?
Because you have multiple things changing all at once. It's not just atoms moving around. Electrons are physically moving between the atoms, the electrical charges are changing, oxygen levels are shifting wildly, and usually water is being produced or consumed as a byproduct of the whole thing. Trying to balance the coefficients, those numbers in front of the molecules by hand, is an absolute nightmare. You end up in this infinite loop of erasing and rewriting. You finally fix the oxygen, but doing that breaks the hydrogen. You fix the hydrogen, and now your electrical charge is completely wrong.
So the professor basically just says stop doing it by hand.
Exactly. He introduces them to Excel's solver add-in. In Ukrainian, he calls it poshukreshenia, which translates to the search for solution.
And this goes right back to that top-down versus bottom-up idea, right?
It does. A bottom-up way to solve this specific problem would be writing a Python script completely from scratch, where you tell the computer explicitly how to calculate every single atom's movement. It's slow, it's highly complex, and if you make even one tiny typo, the whole thing breaks.
In the top-down way.
You use a tool that is already significantly smarter than you. Excel Solver is a dedicated optimization engine. You just need to know how to ask it the right question.
Let's visualize this for the listener, because I found the visual setup here fascinating. He doesn't just type H2O plus CO2 into his spreadsheet cell. He builds a full matrix.
Yes. Imagine a standard spreadsheet grid. The rows represent the chemical elements. So you have a row for potassium, a row for chromium, a row for oxygen, and a row for hydrogen. The columns represent the chemical compounds involved in the reaction.
Okay, so let's say I have potassium dichromate as one of my reactants. That gets its very own column.
That is one column, yes. And where that column intersects with the potassium row, you just type a 2, because there are 2 potassium atoms in that specific molecule. Where it intersects with oxygen, you put a 7. You are directly translating the physical molecule into a column of raw numerical data.
So you turn the messy chemistry into a neat grid of numbers. Then what happens? How does Excel actually know what to do with that grid?
Then you set up a target function. This is the ultimate goal you give the computer. Since matter cannot be created or destroyed, the mass of the reactants minus the mass of the products must equal 0.
So the computer's only job, its only goal is just make this 0.
Exactly. The computer doesn't know what chemistry even is. It doesn't know what oxygen is. It certainly doesn't care if it blows up the virtual lab. It just sees a pure math problem. It starts frantically adjusting the amounts of each compound, changing the coefficients over and over, trying to get that final subtraction to hit exactly 0.
It's just brute forcing the balance.
It's pure optimization. And it usually finds the correct answer in a fraction of a second.
But this leads to what I'm calling the mystery of the missing chromium. There's this really great moment in the recording where they are debugging a student's screen, a student named Alexander.
This was a fantastic detective moment to listen to. They are looking at this matrix, and the columns aren't labeled with helpful names like water or oxygen.
Yeah.
They just say X2, X3, X4. It is completely abstract.
And the professor points to column X3 and just asks, "What is this?" And Alexander just looks at the raw numbers and says, "That's bromine gas. Br2.
And how did he know that? Because in that entire column, the only non-zero number was a 2, sitting right in the bromine row. Everything else in the column was a 0. He was reading the matrix code the same way you'd read the green code in the Matrix movie.
But then I noticed something kind of weird. The professor actually flags it too. This is a reaction involving potassium dichromate. It definitely has chromium in it. And the stuff they're making at the end, the product, also has chromium in it.
Right. You obviously can't have a reaction with chromium without chromium being involved somewhere.
But in the matrix they're looking at, the chromium row looked like it was being completely ignored, or it was zeroed out. It was just empty.
It wasn't ignored, it was canceled out. This is a beautiful example of mathematical efficiency that, frankly, confuses a lot of people at first.
Explain that for me. If chromium is important to the physical chemical reaction, how can the mathematical model just drop it entirely?
Think about it like a bank account. Imagine you have a really weird rule with your bank that says every single time you deposit a check, the bank charges a processing fee that is exactly equal to the check amount.
Okay, that sounds like a terrible bank, but I'm following you. So I deposit $100, the bank takes $100.
Right. What is the net change in your balance?
0.
Exactly. Does the bank's central computer need to know why you deposited the money or even what the currency was to know that your overall balance didn't change? No. In this chemical reaction, the stoichiometry happened to be such that the exact amount of chromium going in was mathematically identical to the amount coming out, based purely on the fixed ratio of the other elements.
So because the variable was identical on both sides of the equation.
The solver algorithm effectively says this variable doesn't influence the imbalance. It's a wash. I can safely ignore it to solve the rest of the puzzle much faster. It simplifies the system entirely automatically.
That is ruthless efficiency. It's like the algorithm is just saying, I don't care about your little details, I only care about the final outcome.
It is ruthless. But the professor also warns them about a major trap here. He says sometimes the solver gives you an answer, but it's messy. It gives you weird decimals, like it'll say, you need 1.5 molecules of water.
Which in actual chemistry is impossible. You can't have half a molecule. That's like saying you have half a person.
Right. He calls this formal verification. If the solver can't find clean, whole numbers, integers, or if it just returns total nonsense, it's not because the computer's broken, it is because you broke reality.
You set up the initial problem wrong.
Exactly. Usually it means you forgot a product. Like you completely forgot that the reaction produces water as a byproduct. If you leave a crucial piece of the puzzle out, the math can never balance to 0 using whole numbers.
I love that concept. The computer is basically telling you, I cannot solve this because your fundamental understanding of the world is flawed.
It's a harsh feedback loop, but it forces you to deeply understand the chemistry. You can't just guess your way through it. You have to verify your model against reality.
So we've modeled the reverse osmosis unit, we've hacked the matrix to balance the atoms, but then, right toward the end of the recording, the professor completely shifts gears. He stops talking about math entirely and starts talking about English.
And honestly, this is where we see the master's level mindset really shine through. He takes the exact same active modeling philosophy and applies it directly to learning a language.
He goes after a very popular learning method, too. He basically tells the class, stop watching Netflix.
Yeah, he is extremely critical of passive consumption. He argues that watching movies or listening to pop songs in English is a trap.
But wait, everyone recommends that. I feel like every single language app out there says immerse yourself, watch Friends without the subtitles on. Why does he say it's useless?
He calls it passive learning. He says, sure, you might recognize a few words here and there, you might get used to the general sound and rhythm, but your brain isn't building the required neural pathways to actually generate language. You are just receiving data, you aren't processing it.
It's the difference between looking at a toilet tank and actually building one.
Exactly. You can stare at a toilet all day long, but that doesn't mean you can engineer the valve mechanism. To learn, you have to build. And to learn a language, you actually have to speak it.
So what does he suggest they do instead? Because speaking is hard, especially if you're shy or self-conscious.
He advocates for something called CLIL, Content and Language Integrated Learning. The idea is simple, but incredibly demanding. You must speak about your actual professional tasks in the new language.
So instead of learning how to say generic tourist stuff like where is the library or one coffee please, you should be trying to explain the toilet tank model in English.
Precisely. If you are an engineer, you need to speak about engineering. If you are complaining about the power outage in Rivne, complain about it in English. Use the language to do your actual daily work. He says you need to integrate it into your real life, not treat it as a separate subject you just study for 20 minutes a day on your phone.
He gives a really specific test for fluency during this part, which I actually tried on myself and failed miserably, by the way.
You mean the thought translation test?
Yeah. He says, catch yourself right in the middle of a mundane thought in your native language. Maybe you're thinking, I wonder if this coffee is too hot, or I really need to email my boss about that report. Can you immediately, right in that very second, express that specific personal thought in English?
It is a really high bar. It forces you to move away from rehearsed phrases, which is what most language apps teach you, and move toward real-time processing.
And he admits it's scary. He uses the Ukrainian slang word striomno, which means sketchy or frightening. It's the universal fear of looking stupid in front of people. But he offers a really modern solution for the shy folks out there.
He brings up AI. He specifically mentions tools like NotebookLM and Grok.
Which is incredibly meta, considering we are currently an AI simulation canalizing his suggestion to use AI.
It is a bit meta, but think about why he suggests it. If you are a student sitting in a war zone, maybe you don't have a native English speaker sitting next to you to practice with. Or maybe you're just too embarrassed to make grammatical mistakes in front of your brilliant professor.
So he just says, talk to the bot.
Right. Upload your complex lecture notes into NotebookLM, and then just have a conversation with it in English about the chemistry. The AI isn't going to judge your accent. It's not going to laugh at you if you completely mess up the verb tenses.
It's a sandbox. You can build your language model, test it out, crash it, and fix it, all in total safety.
And crucially, you are learning the chemistry and the language simultaneously. That is true active learning. You are forcing your brain to encode the exact same information twice. Once for the math logic and once for the English vocabulary.
So we've gone from a gritty lecture hall in Ukraine, through the abstract logic of matrix math and the mystery of the disappearing chromium, all the way to a unified philosophy of active language learning. It is a lot to unpack for one session.
It is, but I really think there's a strong unifying thread running through all of it.
What's that?
It's the fundamental difference between being a passenger and being a pilot. The student approach, the passenger approach, is to just copy the data, follow the instructions, watch the movie, fill in the cells on the spreadsheet because you were told to.
Passive. Just sitting there waiting for knowledge to happen to you.
Exactly. Completely passive. The master's approach, whether it's modeling a chemical plant under shellfire or speaking a brand new language, is about understanding the underlying system. It's about building the model yourself from the ground up. It's about total engagement.
You aren't just memorizing the final answer. You are building the solver yourself.
Exactly. And that mindset applies to absolutely everything we do.
That is a genuinely great place to leave the main discussion. But before we wrap up, I want to leave you, the listener, with a thought inspired by that missing chromium.
The variables that cancel out.
Exactly. We all have things we stress about constantly. In our workflows, in our big projects, maybe even in our personal lives. We spend hours and hours trying to calculate and balance them. We worry about every single little detail. But maybe we need to look at our own matrix again.
Ask yourself, does this variable actually change the final outcome?
Or is it just chromium? Maybe, mathematically speaking, it simply cancels itself out in the grand scheme of things. Maybe you should let the solver of life just ignore it, so you can focus all your energy on the variables that actually matter.
That is a very freeing thought. Just let the solver do the work.
Thanks for taking this deep dive with us today. We'll catch you next time.
See you next time.